Trigonometric substitution. To evaluate integrals involving the square root of a number squared plus x squared, the square root of a number squared minus x squared, and the square root of x squared minus a number squared, it sometimes helps to make what's called a trigonometric substitution. So how do you know what trig substitution to make? Well, here's a table that you'll want to know. If your integrand involves the square root of a squared plus x squared, the substitution that you're going to make is x equals a tangent theta, and all of these do have these built-in restrictions involved. If you have the square root of a squared minus x squared, the substitution is x equals a sine theta, and if you have the square root of x squared minus a squared, the substitution is x equals a secant theta. In this first example, we have the integral of 1 over x squared times the square root of 16 minus x squared dx. So here, if we were to kind of try a u substitution and let u be the part underneath the square root, we'd end up with the derivative of negative 2x, and we have 1 over x squared, so that doesn't work. So here, when we see a square root with 16 minus x squared under it, so an a squared minus x squared, we're going to think trig substitution. Now, to sort of help you think about which trig substitution, I'm going to do a quick example up here where, let's say I had to evaluate the integral of 1 over the square root of 16 minus x squared dx. So almost the same integral except minus this x squared piece right here. So I'm removing the x squared in front. Well, this problem actually has a general antiderivative. If we look at our table of general antiderivatives, this would become arc sine of x over 4 plus c, because 16 is 4 squared minus x squared. So we do have this general antiderivative here, and it is arc sine. So that can help you figure out which substitution to make. So the square root of a number squared minus x squared, just like here, a number squared minus x squared became arc sine. The substitution that we're going to make is a sine theta. So what we're going to go ahead and do is let x equal 4 sine of theta, where there is this built-in restriction that theta is between pi over 2 and negative pi over 2, and we'll see how that kind of comes into play a little bit later. So if we let x equal 4 sine theta, then if we go ahead and take the derivative, then dx is 4 cosine theta d theta. So what that would allow us to do is replace, so far, each of these two x's with 4 sine theta and replace dx with 4 cosine theta d theta. So let's go ahead and do that. So this right here is like our scratch work so far. So our integral is about to become 1 over, instead of x squared, it's 4 sine theta squared, then the square root of 16 minus the quantity 4 sine theta squared. And then dx is 4 cosine theta d theta. So we've replaced everything here to be in terms of theta. So now let's see how that helped us. So the 4 cosine theta d theta, I'll go ahead and move that to the top. So we'll just slide it over, 4 cosine theta d theta. On the bottom, I'm going to square each term. These are multiplied, so I can square each part. So I get 16 sine squared theta. And then underneath the square root, I have 16 minus 16 sine squared theta. So the 4 gets squared and the sine gets squared. All right, so from here, I can do a couple things. So I can cancel the 4 into the 16. So the 4 will disappear. This 16 will become a 4. And then underneath this radical, they both have a 16 in common, so I can factor it out. So I have cosine theta on the top, I have so far 4 sine squared theta, then the square root of 16 times 1 minus sine squared theta. There's a d theta there. Alright, so now, since these are multiplied, 16 times 1 minus sine squared theta, I can take the square root of each part. So the square root of 16 is just positive 4. So what's going to happen here is I'm going to have this cosine theta d theta still. I have 4 sine squared theta. And then the square root of 16, as I said, is positive 4, so there's a positive 4. And then what I have left is the square root of 1 minus sine squared. Well, we have a Pythagorean identity here that says that 1 minus sine squared is cosine squared theta. So I'm doing kind of two things at once here. The square root of 16 is 4, I'm pulling that out. 1 minus sine squared is cosine squared. So I'm going to leave the cosine squared theta underneath the radical. All right. So now I have the square root of cosine squared theta. Now here, because we're on this restricted interval, where theta is between negative pi over 2 and pi over 2, we can go ahead and say that the square root of cosine squared theta is just cosine theta. So in other words, we can say that the square root and the squared cancel because we are on this appropriate restricted domain. Because in general, if I have the square root of x squared, it's not just x, so just like quick review, if I have the square root of x squared, that's not always x. So the only time it equals x is when x is greater than 0. So there is a restriction there. So in this case, I can cancel it out because it does work over this restriction. So now let's go ahead and see where that leaves us. So I'm going to go ahead and kind of pull this work up here. So I have the integral of cosine theta d theta over 16 sine squared theta times just cosine theta, because the square root and the squared cancel. Alright, so now the cosine theta on the top cancels with the cosine theta on the bottom. So we've gotten rid of that, and what we can do is pull out the 1 over 16. We can pull out that coefficient. And so what I'm integrating is 1 over sine squared theta d theta, which is cosecant. So the integral of cosecant squared theta d theta is actually nice. We have a general antiderivative for this. So that's going to give us negative 1 over 16 cotangent theta plus c. Now, we've got to a point where it was something we could easily integrate, and that's the idea behind the trig substitution, that we have some identities to work with, some trig identities to work with to kind of cancel, and leave ourselves with, hopefully in the end, something nice to integrate. But it is going to leave us in terms of theta, and our original integral is in terms of x. So we have to go ahead and make sure that we convert this, change this, into a function of x. To do that, I'm going to come back over here to our substitution. We let x equal 4 sine theta. So what I'm going to go ahead and do is, down here, rewrite that as x over 4 is equal to sine theta. So I'm just going to go ahead and divide by 4. So what we know here is that sine of some angle theta is equal to x over 4. Well, we know sine is opposite over hypotenuse. So I'm going to construct myself a triangle, a right triangle, with an interior angle theta. And what I know about theta, sine, is opposite, so the opposite side of theta is x, and the hypotenuse is 4. Well, I want cotangent of theta. I want essentially cotangent of theta. So cotangent is adjacent over opposite. because tangent is opposite over adjacent, so cotangent is adjacent over opposite. So I'm going to need this adjacent side right here, the adjacent side to theta. Well, that just means I'm going to go ahead and apply the Pythagorean theorem here to find this missing side length. So let's call this missing side length for a second b. So we know that b squared plus x squared equals 4 squared. So b squared is equal to 16 minus x squared, or b is equal to plus or minus the square root of 16 minus x squared. Well, we're talking about a side length here, so we're going to have positive the square root of 16 minus x squared as our adjacent side. So cotangent, again, is adjacent over opposite, so I'm going to go ahead and replace this cotangent theta with the adjacent side, radical 16 minus x squared, over the opposite side, x. And then what we have in front still is the times negative 1 over 16 plus c. So we can write this as negative radical 16 minus x squared over 16x plus c as our answer. In this example, I want to integrate x squared dx over the square root of the quantity 4 plus x to the 6th. If I try a traditional u substitution where I let u be the entire thing under the square root, 4 plus x to the 6th, that's not quite going to work. That'll give us 6x to the 5th, and I have an x squared up here. But what I can hopefully recognize is that I can think about this as x squared dx all over the square root of 4 plus the quantity x cubed squared. So what I can do is let u equal x cubed, and then du is 3x squared dx. I only want an x squared dx, so I'll divide by 3. 1/3 du is x squared dx. And then what we have is the integral of 1/3 du, and then over the square root of 4 plus u squared. Now this is set up for me to go ahead and apply a trigonometric substitution. So this does not have a general antiderivative because of the square root. So if the square root was missing and I just had a number in front, so the 1/3, we can think about it in front, du over 4 plus u squared, this would become arctangent or tan inverse. But because of the square root, I can't do that. But what I can do is a trig substitution. So the trig substitution is going to be letting u, since it's all u's now, we're going to go ahead and let u equal 2 tangent theta. So the 2 comes from the fact that we're doing 4 plus u squared, so the value of a is 2. So now the derivative of this is going to be du equals 2 secant squared theta d theta. And like before, the restriction on this theta is between negative pi over 2 and pi over 2. Alright, so now we can go ahead and do our replacements here. So what we have is, make a little bit of space. This is all scratch work. I'm going to work vertically here. So I'm going to pull out the 1/3, and then du gets replaced with 2 secant squared theta d theta all over the square root of 4 plus the quantity 2 tangent theta squared. So what we can go ahead and do now is I can pull this 2 out to the front, so I have 2/3 the integral of secant squared theta d theta. Underneath the square root is 4 plus 4 tangent squared theta. I can take a 4 out of each term here, So I have 2/3 the integral of secant squared theta d theta all over the square root of 4 times 1 plus tangent squared theta, all in parentheses. Now, the square root of 4 is 2. I can take the square root of 4 because it's being multiplied here. And then 1 plus tangent squared, that's an identity. So 1 plus tangent squared is secant squared. So I'm going to go ahead and bring this kind of up to the top to make some space. So what I have is 2/3 in the front. What's going to join it in the front is a 1/2. Because the square root of 4 is 2, but 2's in the denominator. So I have 2/3 times 1/2. Those 2's will cancel. And then the integral of secant squared theta d theta over the square root of secant squared theta. So I replaced 1 plus tangent squared with secant squared, the Pythagorean identity. And the square root of secant squared, it does cancel because I'm on that restricted domain. So it's the restricted domain that's going to allow us to do that square root and square canceling here. So then what I'm going to have left to integrate, I have a 1/3 in the front, and I'm just going to have a secant theta d theta left to integrate because the bottom will be just 1 secant. It will cancel with one of the secants on the top, leaving us with secant theta. Now this is one of the integrals that we wanted to have memorized because it does come up so often. So we'd have 1/3, and then the general antiderivative of secant is natural log of the absolute value of secant theta plus tangent theta plus c. And now all that's left to do is turn us back into x. So we're currently a function of theta, and we need to be a function of x. Well, we're going to have to kind of take 2 leaps to get there because I had u equals 2 tangent theta, and then I'll have to get back to x because we did a u substitution. Alright, so the first thing is I'm going to go ahead and rewrite this as u divided by 2 is equal to tangent theta. And so that's going to currently let us replace tangent theta with u over 2, so that's not too bad. So tangent theta right now is going to get replaced with u over 2. And then I'm going to need to replace secant theta. Now to do that, I am going to need to draw myself a triangle. So I'm going to go ahead and draw a triangle, knowing that this right triangle has the trig relationship that tangent of theta, so if this is theta, tangent of theta is opposite over adjacent. So we have u over 2. And I want to find secant theta, which is the reciprocal of cosine. So cosine is adjacent over hypotenuse, so we're going to need hypotenuse over adjacent. We're going to need the hypotenuse, which is taking each of these sides, 2 and squaring it, and u and squaring it, and then taking its square root. So the square root of 4 plus u squared. So we're just applying the Pythagorean theorem, but I did it a little quicker this time. So now, again, secant is going to be hypotenuse over adjacent. So we have the square root of 4 plus u squared over 2. And now I'm going to go ahead and bring everything else down. The last step is, now that I'm in terms of u, I'm going to replace u with x cubed. So I have 1/3 the natural log of the absolute value of the square root of 4 plus x to the 6th over 2, because I'm plugging in x cubed and squaring it, so x to the 6th, and then plus x to the 3rd over 2 plus c. In this example, we want to integrate the square root of 9x squared minus 63 all over x. So here what we have is this 9 in front of x squared. And in order to use a trig substitution here, and we're thinking trig sub because if I let u be the part underneath the radical, 18x would be the derivative, and I don't have an x, I have a 1 over x. So we're thinking trig sub, and in order to do a trig sub, we need that leading coefficient right here to be a 1 if we're thinking about using the a secant theta trig substitution. So what I'm going to start doing is factoring the 9 out of each term here. So I have the integral of the square root of 9 times x squared minus 7 over x. And because I created a product, I can take the square root of each part, so the square root of 9 is 3. So I can go ahead and take the 3 out. And now I have the square root of x squared minus, I'm going to write this as radical 7 squared all over x. So I typically have perfect squares, but I don't have to. I can rewrite this as x squared minus the square root of 7 squared, a number squared. And then from here, perform my trig sub. So since x squared is first, and then it's minus a number squared, we're going to go ahead and use the secant trig sub. So we're going to let x, because we're going to replace x, so we're going to let x equal a. Well, the value of a is radical 7, so radical 7 secant theta. And then the derivative, so dx would be radical 7 secant theta tangent theta d theta. So here's going to be my scratch work where eventually I will need to create a triangle. And so we're going to replace our x's and our dx, which we can't forget the dx because then we can't replace that whole thing with everything we need to have a d theta in there as well. So now I'm going to go ahead and make my substitutions. So I have 3, the integral of the square root of x squared, so that was radical 7 secant theta squared minus, let's just go ahead and leave that as 7, and then over x, well, x was radical 7 secant theta, and then dx is radical 7 secant theta tangent theta d theta. So we're going to have some nice things happen, and hopefully you start to recognize that, there are some nice things that are going to cancel out, and we're going to be able to use these Pythagorean identities. So here, because everything is multiplied, I'm going to cancel out the radical 7s. Radical 7 over radical 7 is 1. Secant theta over secant theta is 1. And then underneath here, underneath the radical, I have the square root of 7 secant squared theta minus 7. And then over, well, really over 1, right? Everything there is gone. And then I just have a tangent theta d theta. So what I'm going to do is I'm going to factor out the 7 here. So let's go ahead and move this up. So we have 3. I'm going to factor out the 7. So I have secant squared theta minus 1. I don't know why I'm still writing it as if it's like in a numerator. Since it's over 1, let's just put it in the middle. And then times tangent theta d theta. There we go. Alright, so now the square root of 7 and then times the quantity secant squared theta minus 1. Well, secant squared theta minus 1 is a Pythagorean identity. It is tangent squared theta. And then here, I'm going to take the square root of 7, which isn't a perfect square. We're just going to have the square root of 7 multiplied by the 3 in front. And then I'm going to have the square root of tan squared theta times tangent theta d theta. And here, one of the things I didn't go ahead and write down, but it does hold true, is that our substitution had a restriction, and because of that restriction, we are able to say that the square root of tangent squared cancels, and it's just going to leave us with one copy of tangent. So tangent times tangent is tangent squared. So that's what we are integrating. Tangent squared theta d theta. All right, well, tangent squared theta doesn't have a general antiderivative. So now we have to start thinking about, well, how do I integrate tangent squared? Well, tangent squared, as we just used a second ago, is equal to secant squared theta minus 1. And that is going to be helpful. So if I replace tangent squared theta with secant squared theta minus 1, now I can integrate each part separately, and each part does have a general antiderivative. The antiderivative of secant squared, or the integral, is just tangent, and the integral of 1 is just theta. So we have 3 radical 7, and then tangent theta minus theta plus c. So the only thing left to do now is to turn our thetas into x's, because that was the original variable. So we come back over here, and we can go ahead and write this as x over radical 7 is equal to secant theta. And this is going to be something new that we do. We are going to draw a triangle eventually in a second to rewrite tangent theta, but we also have this theta here. So how do I just get theta to turn into something involving x's? Well, here, in order to get this theta by itself, I'm going to go ahead and do secant inverse of both sides. So essentially, we're going to end up getting that secant inverse of x over radical 7 is equal to theta, because secant of secant inverse is going to cancel out. So I can replace this theta with secant inverse. So we have 3 radical 7. I'll just go ahead and leave that there. Leave a space for what tangent's going to equal, and then minus secant inverse of x over radical 7. X parentheses plus c. And so now we just have to find tangent theta. So for that, we can go ahead and construct our triangle. So here's our right triangle. Secant is x over radical 7. Well, secant is the reciprocal of cosine, so cosine is adjacent over hypotenuse. So we're going to have hypotenuse over adjacent. So we have x over radical 7, and then we are going to want tangent, which is opposite over adjacent, so we're going to need this other side length. And so I'm going to skip doing kind of that work for the Pythagorean theorem. It's going to be the hypotenuse squared minus the side length squared, so that's just 7. So the square root of x squared minus 7. So we have opposite over adjacent to replace tangent theta, so the square root of x squared minus 7 over radical 7. And because these are both square roots, I mean, we could put just one big square root with a quotient underneath, but that's fine. I'm just going to go ahead and leave my answer like this. And one of the things that I do kind of see sometimes is students will go, okay, well, I can just find theta by doing, you know, the inverse trig function here, so why not just replace this theta with secant inverse? Well, because we can do better, basically. So if we can turn a trig function into its algebraic representation, that is better than leaving it as a trig inverse, because then you would have written your answer as tangent of secant inverse of x over radical 7, which is ugly, right? It's not something that we'd ever want to like evaluate. If this was a definite integral, we'd prefer algebraic functions over trig inverse functions. Alright, in this next example, we're going to add a couple of things. We're going to evaluate a definite integral. So the integral of 1/2 to 1 of the quantity 1 minus x squared, all raised to the 3/2 over x to the 6th. So as I said, we have a definite integral, we have limits of integration. And then here we do have a square root, because to think about using trig sub, we do need a square root. we just have it written a little bit differently. So instead of a square root, we have written as a quantity to the 3/2, which is taking a square root and then cubing it as an entire quantity, and then over x to the 6th. So here we are going to do our trig sub using the sine function, because we have 1 minus x squared, and the value of a is 1. So I'm going to get started by saying we're going to let x equal just 1 sine theta, and that restriction was negative pi over 2 to pi over 2. And so dx would be cosine theta, d theta. And let's go ahead and start replacing a few things. I'm going to hold off on the limits of integration. I'm going to go ahead and substitute in sine squared theta, or sine theta for x squared, and then that's raised to the 3/2. And then over, this would be sine to the 6th theta, and then dx would get replaced with cosine theta, d theta. So these limits of integration, they're going to add an additional piece that we have to handle. If we remember that these are x values, so x equals 1/2 to x equals 1, that's going to help us think about how to rewrite them so that they are theta values. So we're going to need them to be thetas to carry them on through the problem. So here, the relationship between x and theta is that x equals sine theta. So if I replace 1/2 with x, so going ahead and moving this down here, 1/2 is equal to sine theta. Well, then what I can go ahead and do is recognize, well, this does have infinitely many solutions, but we're on this restriction between negative pi over 2 to pi over 2. And so the one value that is going to work is theta equals pi over 6. So sine of pi over 6 is 1/2. So we can go ahead and replace that. And then if x is equal to 1, then we have 1 is equal to sine theta. And on that restriction, we have that theta must equal pi over 2. So now we can go ahead and move forward. So we have 1 minus sine squared theta, that's cosine squared theta. So we have the integral from pi over 6 to pi over 2. We have cosine squared theta. And this is raised to the 3/2, but what I'm going to go ahead and do is rewrite it as the square root, and then all cubed, and then over sine theta all to the 6th power, and then times cosine theta d theta, just so that I can see how the square root and the square are going to cancel. And we especially know that this works on this domain restriction because we're between pi over 6 and pi over 2, so that's within this interval. So what I have left is cosine theta, but cubed, and then there's an extra cosine theta, so we're looking at the integral from pi over 6 to pi over 2 of 4 copies of cosine theta, and then over those 6 copies of sine theta d theta. Alright, so to go from here, we want to think about how to integrate cosine to the 4th over sine to the 6th. And traditional u substitution isn't going to work. So what I'm going to have to do is kind of cleverly rewrite this. So this would be pi over 6 to pi over 2. And I want to think about this as cosine to the 4th over sine to the 4th. And then that's going to leave me 2 extra copies of sine, a sine squared theta. And then there's just a 1 being multiplied over here, d theta. So what I can now do is write this cosine over sine as cotangent to the 4th power. So I'm bringing this up here. So I'm going from pi over 6 to pi over 2 of cotangent to the 4th theta. And then 1 over sine squared is cosecant squared theta d theta. And this is able to be solved by doing a traditional u substitution, because if I let u be cotangent, the derivative of cotangent is cosecant squared, or negative cosecant squared. So I'm only off by a negative. So let's go ahead and do a u substitution over here. So let's let u be cotangent theta, then du is negative cosecant squared theta d theta, and then negative du is cosecant squared theta d theta. But these values are thetas. I'm going to have to turn them into u's. So I'm going to go ahead and do that all at once as well. So what is u of pi over 6? So that's what is cotangent of pi over 6. That's radical 3. And then we're going to do what is cotangent of pi over 2, and that's 0. So let's see, pi over 6 corresponded to radical 3, pi over 2 corresponded to 0. We are going to have a negative in front, and then we have, let's see, just u to the 4th du, because I'm going to replace my cotangent theta with u, and then cosecant squared theta d theta with negative du, so put the negative in the front. I want my smaller number to be on the bottom for the limits of integration, so when I flip it, we'll get rid of that negative. 0 to rad 3 of u to the 4th du, and so that's going to be 1/5 u to the 5th evaluated from 0 to radical 3. So if I go ahead and plug in the radical 3, I have 1/5 and then radical 3 to the 5th. And to simplify this even further, I can take radical 3 to the 4th, which would be 9. Radical 3 times itself 4 times is going to give me 9. So I could write this as 9 radical 3 over 5. So because at each step of the way I changed my limits of integration. When I did a trig substitution, I changed them into thetas, and then when I did a u substitution, I changed them into u's, right? So this was u equals. I never had to go back and draw a triangle or go back and do anything to get myself back in terms of x, because this was a definite integral.